Hello and welcome to No Effort November, a series of videos for the month of November where no effort is made.
This is Alec Watson from Technology Connections. He has a tradition on his channel where he puts zero effort into videos produced in the month of November. I'm following suit with this tradition since it has been quite a busy month for me, so apologies if the voiceover or editing is flakier than usual. In any case, I thought I would make a behind-the-scenes video on how I made the lights flicker in my Halloween special video. Alright, so I've quickly thrown together a block diagram of what I've set up. Now before we get into how I got the lights flickering, let's try to simplify things a little bit. You see the contactor and the battery charger I was using to power it? Well, that part was for show more than anything else, since it had no effect on anything after I had hooked it up. For those who don't know what a contactor is an electromagnetic switch. At the bottom, there is a coil which, when energized, turns into an electromagnet, which sucks in the contacts and closes the circuit. Since the power to the contactor coil was never lost during the experiment, we can just ignore that any of it existed. It might as well be directly wired like I had originally planned. If you want to find out more regarding how a contactor works or what it's used for, Alec Watson from Technology Connections has a video just for that. Now before we keep going, here's a trick question. What does this symbol mean? A. Normally open contact. B. Non-polarized capacitor. C. All of the above. Or D. None of the above. Pause the video to try and figure it out. Alright, believe it or not, the answer is C for all of the above. Here's the thing. In my electrical class, we just wrapped up our motor control unit, and I was very disappointed. On top of the fact that Camel sent us a shorted motor and a whole bunch of defective relays, we were being taught that this symbol was contact, which is complete bull anywhere outside of the United States of redneck engineering. And if you've seen my last video, you'll know how I feel about these American standards.
American standard, more like American non-standard.
There's no excuse for a damn contact to look so similar to a capacitor, especially when many motors have starting, running, and power factor correction capacitors. A capacitor and a contact are very different things, and mixing the two will result in lots of magic smoke and expensive noises. It got to the point where I literally invited the official IEC standards Instagram account into our group chat, and then proceeded to destroy said group chat with pro-IEC commentary. The IEC, or International Electrotechnical Commission, is an internationally recognized standards organization based in Geneva, Switzerland, that governs international standards pertaining to electronic and electrical related technologies. Did you read through that satire dictionary that I showed you earlier? This is a map of territories that observe the quote-unquote International Building Code, and this is a map of International Electrotechnical Commission member states. Big difference in the meaning of international, in case you somehow didn't notice. And as a bonus, here's a map annotated by a fellow European. As a side note, here in Canada, we have our own building code, but at least we don't have the audacity to call it international and expect the rest of the world to adopt it. Alright guys, quick little thing here. In our electrical class, we are starting our electronics unit soon, and to be honest, this thing doesn't even remotely deserve to be called an electronics textbook. They literally only talk about a couple types of diodes and BJT transistors, not even MOSFETs, which is a complete insult to the name of this channel. At the bare minimum, an electronics textbook should be something that's about this thick. They also do their worst to promote designing circuits with electron flow, which is completely ridiculous from an electrical engineering standpoint, since we always use conventional current for circuit design.
When we design electronic circuits, we use conventional current. So in this NPN transistor circuit, we assume that the current is flowing from the battery's positive into both the collector and the base pin, and then out of the emitter pin. We always use this direction to design our circuits.
Man, these are all frickin' upside down. Man, they must have written this piece of in the 80s or something before blue LEDs were invented. They also make the same error of using a capacitor symbol for a relay contact, which is something you just don't do in electronic schematics. Also, this electronics textbook has the same ordeal with the electron flow and the NEMA-inspired schematic symbols. It also references the NEC, which ultimately means that it will collect dust on the shelf for a long time to come. Alright, let's get back to figuring out how I made the lights flicker. So it wasn't the contactor powering the motor that made the lights flicker, then what made the lights flicker? The secret lies in this little mystery box that I opened up for the video. You see, these fan motors were scavenged from 240 volt air conditioning units, but here in North America, we typically use 120 volt outlets. So how do they manage to get these fan motors to run? Here's a crash course on the North American residential electrical system. Like most homes around the world, we get single-phase power, but since Thomas Alva Edison was American, our homes get power using a modern alternating current version of the Edison 3-wire system. Basically, the utility transformer supplies 220 volt lines that are 180 degrees out of phase with respect to the neutral, creating a difference of 240 volts between the lines. These two lines come into your panel, and the various outlets in the house are fed from either of the two lines in neutral for 120 volts. Yes, the two lines are technically in phase, and yes, the graph I chose was labeled an RMS voltage instead of peak voltage. Not too important of a distinction for the general audience, but I need to include that so that the nerds who are watching won't completely wreck the comment section. If you require further clarification on how the North American residential electrical system works, Alec Watson from Technology Connections also has a video covering that. This mystery box is a poor man's version of a product known as a Quick 220, which makes 240 volts using 220 volt outlets on opposite phases. Fun fact, I salvaged this electrical box with this relay out of the dumpster at my school a little over a year ago, and custom made these brackets here when I was taking automotive class. Unlike the official Quick 220, which is a relatively safe and idiot-proof product, this thing is a potential shock hazard if you don't know what you're doing. Obviously, it's still a lot better than the contraption that Electrical made a while back, since it has a breaker and a relay.
Here we are. Every wire of the outlet is connected to the live of one of these plugs. And even if we just plug in one of them, it is still safe to touch the other one because it's not connected anywhere. Now if we connect the hairdryer... I was wrong. If you plug in a hairdryer that's on, the live voltage will travel through the hairdryer to the other plug. So this is live now. It's only safe if you plug both of them in first and then plug the hairdryer.
If you plug the one end in and turn on the breaker, the other end becomes energized at 120 volts through the relay coil, as you can see here. See? Ow! As I was saying, the other end becomes energized at 120 volts through the relay coil, which is something that I overlooked when I was initially designing this thing. And to clarify, a relay is more or less the same thing as a contactor, only smaller and rated for less power than a contactor. Alright, at this point, most of you should have probably figured out which component was causing the lights to flicker, but you are still probably figuring out why the circuit would behave like this. So I've gone ahead and simplified the block diagram into a schematic diagram that we can follow using IEC inspired symbols where possible, because screw NEMA! Notice that L1 is being switched with the room lights. This is what the orange extension cord in the video was connected to. Like in the video, the lights were already on, but the motors were off. We'll assume DC current to keep the drawing simple. After all, it's no effort November, and I am definitely not making an animation to represent AC current. The room lights were already on as normal, and 240 volt is applied to the relay coil when I close the breaker, causing the relay contact to close and turn on the fans. At this point, everything in the circuit is stable and operating normally. In order to cause the mayhem at the end of the video, I turn off the room lights using the switch behind me, which is this switch right here. This causes the current to flow backwards from L2 through the relay coil and motors, through the lights and back to neutral. When this happens, the low resistance of the fan motors in parallel with the relay coil allows some of the lights to stay on, but this causes the voltage across the relay coil to sag, opening the relay contacts. When this happens, the low resistance motors are no longer a part of the circuit, and not enough voltage is applied to the lights, causing the lights to turn off. At the same time, the voltage across the relay coil rises, closing the contacts for the motors, and the process repeats all over again. This oscillation is what causes the relay to aggressively chatter while the room lights flash. In reality, a lot more factors are at play here, such as the capacitive inductive effects of the motors and capacitors, as well as the harmonics of the power supplies integrated into the fluorescent and LED lighting. By the way, stay tuned for a future video about lighting technologies coming sometime in December. And with that, this video is finished.